Okay, so in this section, we are going to talk about integration of 1 over x and 1 over ax plus b type of integration. Okay, recall the previous time when we talked about the power rule for integration and also the reverse chain rule, right? We always emphasize that the power rule and the reverse chain rule do not apply for power -1. Okay, so now we're going to talk about how we deal with power -1 in this section. Okay, so integration of 1 over x is essentially the x to the power of -1 case, and 1 over ax plus b is the case where it is ax plus b to the power of -1. Okay, so because the reverse chain rule and the power rule don't apply for these -1 powers, right? Okay, so how are we supposed to integrate this? Okay, recall in differentiation, right? Okay, where do you see the 1 over x? It's when you differentiate ln x, right? Your natural log x. Okay, so when you differentiate ln x, you actually get 1 over x over here. So therefore, integration as a reverse of differentiation means when I integrate 1 over x, I will get back ln x. Okay, so that's why when I integrate 1 over x, I'm not going to use the power rule. There's no such thing as power rule for -1 powers. Okay, so I am going to use the fact that when I differentiate ln x, I get 1 over x. So when I integrate 1 over x, I should get back ln x. Okay, so when I integrate 1 over x, I will get ln x plus c here. Okay, so that is for power -1. Okay, in the case of 1 over x. Okay, how about ax plus b to the power of -1? Okay, so recall when we do differentiation of ln ax plus b. We will actually write it as 1 over ax plus b, then multiply by the differential of the inside here, which is a. Okay, so that's how we get a over ax plus b. Okay, so the reverse applies when I try to integrate 1 over ax plus b. Okay, I will get ln ax plus b, but divided by a. Okay, so then there will be a plus c here as well. Okay, because if the reverse here, right, when I integrate this part, I will get back this part. Okay, so it means when I integrate a over ax plus b, I will get back ln ax plus b plus c. Okay, and then recall I can take out constants here, right, when integrating. So this is the same as a times of 1 over ax plus b dx. Okay, then when I shift it over, okay, so when I want to find integration of 1 over ax plus b, I will divide both sides by a. So I will then have 1 over ax plus b equals to 1 over a ln ax plus b plus c. Okay, so that's how I get this part over here. Okay, so now over here, just like I said, do not confuse this with your reverse chain rule. Your reverse chain rule only works. It only works for your power n that is not equals to -1. Okay. Okay, now let's look at a few examples, okay, where it will utilize what we have learned so far. Okay, so when I want to integrate 7 over x dx, okay, so always take out the constant, okay, so this will be equals to 7 times of integration of 1 over x dx. Okay, so when I integrate 1 over x, I will get ln x. Okay, so 7 ln x plus c. Okay. Okay, now let's look at the second example here. Okay, so this is in the form of the ax plus b kind of way, right? Okay, so same thing, I'm going to take out this. Okay, so I will take this out, so it becomes -2 times of integration of 1 over 5x plus 1 dx. Okay, so I will put a bigger bracket here. So when I integrate 1 over 5x plus 1, okay, so first of all, I will get ln 5x plus y. Okay, then divide by the differentiator of the inside, which is basically 5. Okay, so divide by 5. Okay, then plus c. Okay, then when I simplify this, I will get negative 2 over 5 ln 5x plus 1 plus c. Okay. Hey, now let's look at a combination kind of question now. Why do I say combination? Okay, let's take a look at this question. Integrate 3 over 2x minus 1 plus 2 over 2x minus 1 whole thing squared. Okay, let's take a look at the difference between these two terms. Okay, so the first term over here is basically my 3 times of 2x minus 1 to the power of negative 1. Okay, there when I have a negative 1, cannot use reverse chain rule. Okay, so therefore, the first one, I'm going to use the ln method. Okay, then how about the second one? Am I going to use the ln for the second one also? This basically refers to 2 times of 2x minus 1 to the power of negative 2. Okay, so since this is not negative 1, I can just use reverse chain rule. Okay, so then for the second one, I'm going to use reverse chain rule. Okay, so integration of 3 over 2x minus 1 plus 2 over 2x minus 1 whole thing squared. Okay, so when I integrate this, okay, let's split them up so that it's clearer. Okay, so I will split these two up into each of the individual terms. So this is integrating 3 over 2x minus 1 dx plus integrating 2 over 2x minus 1 whole thing squared dx. Okay, so I can take out the constants, right? Okay, in both cases. So when I take out the first one, I will get 3 times of integration of 1 over 2x minus 1 dx plus, okay, here I can also take out the constant 2, okay, times of 1 over 2x minus 1 whole thing squared is the same as 2x minus 1 to the power of negative 2. Okay, so the first one, I'm going to use the ln one to integrate it. So 1 over 2x minus 1, when I integrate, I will get ln 2x minus 1 over, okay, the differentiator of the inside, which is 2. Okay, then for the second one, I'm just simply going to use reverse chain rule. Okay, so I will increase the power by 1. Okay, so it becomes negative 1. Divide by the new power. Okay, and also the differentiator of the inside, which is 2. Okay, then don't forget your plus c for integration. Okay, so when I simplify this, I will eventually get 3 over 2 ln 2x minus 1, then minus. Okay, so this 2 cancels each other out. So minus, and then this is a negative power, so I will bring it down. 1 over 2x minus 1 plus c. Okay, so that is your final answer. Okay, so they can also come in this way, where you need to use both the ln method and also the reverse chain rule. Okay, so be very clear when you will use reverse chain rule, when you will use ln. Okay, you will use ln when the power is negative 1. Okay, all other powers use reverse chain rule. Okay, for your algebra. Okay, now let's move on to the second part. Okay, so far, right, all that we've dealt with, right, are what we call proper fractions. Okay, proper fractions meaning the degree, okay, or the power of the numerator is smaller than the power of the denominator. Okay, how about the fact that if I have the numerator and denominator having the same power, or the numerator having a greater power than the denominator, Then before I integrate, right, I need to do long division. Okay, so just take note of this. Okay, so in the case of this example, I have integration of x over 1 plus x dx. Okay, so the degree or the highest power in the numerator is 1. And the highest power in the denominator is also 1. Okay, so they have equal degree, or in the sense equal power. So I need to do long division first. Okay, so that I can split this up. So when I do long division, x divided by 1 plus x, or x plus 1, same thing. Okay, so to make it easier, I will put it as x plus 1. Okay, so when I divide this, okay, add a plus 0 here to account for the constant. Okay, I will multiply by 1 to get x plus 1. Okay, so I will get a negative 1 here. Okay, so essentially it means when I split this up, plus 1. Okay, dx. Okay, so I'm going to integrate this. Okay, so now I've split into two different terms already, right? Okay, so when I integrate 1, I will get x. When I integrate negative 1 over x plus 1. Okay, this part will be my x plus 1 to power of negative 1, right? So I cannot use reverse chain rule here. I need to use log. Okay, so essentially it means when I integrate negative 1 over x plus 1, I will get negative log x plus 1. Okay, then plus. Okay, so now let's look at an example. Okay, together. Okay, so remember when we talk about not having quotient or product rule, right? We need to split them out into individual terms. That is if I can split them out with a common denominator, right? Just one single term as the denominator. When I have two terms at the denominator here, multiplied to each other, how else am I supposed to split them up into each individual fractions then? Okay, then it is the case of using partial fraction. Okay, so first of all, always check if the degree of the top is lower than the degree of the bottom. If it's not, then you have to do long division first. Okay, so in that case, my degree on top is 1, degree bottom is 2. Okay, so therefore it is a proper fraction, so I don't have to do long division. Okay, so I can just use partial fraction to split this up. Okay, so first of all, 2x plus 3 over x plus 1, x plus 2. Okay, so just a recap, these are just linear factors. Okay, so when I split it out, I should get equals to a over x plus 1 plus b over x plus 2. Okay, then when I combine, I will get 2x plus 3 equals to a times of x plus 2 plus b times of x plus 1. Okay, so this one is just simple kind of where I just either want to remove a or b first. Okay, so let's say if I want to remove b first. Okay, so I will let x to be equals to negative 1. Okay, so that this part becomes 0. Okay, so when I let x to be negative 1, I will have 2 times of negative 1 plus 3 equals to a times of negative 1 plus 2. Okay, which essentially means my a equals to 1. Okay, then next to find b, I need to let a to be 0, right? Okay, how do I make this part to be 0 here? It is if I have x equals to negative 2. Okay, so now let x to be equals to negative 2. Okay, then 2 times of the negative 2 plus 3 equals to, now a is gone already, so b times of negative 2 plus 1. Okay, so essentially my b will be 1. Okay, so when I split this out into partial fraction, I would have 2x plus 3 over x plus 1, x plus 2. So therefore, this equals to 1 over x plus 1 plus 1 over x plus 2. Okay, so now that I've split them up into partial fractions, you can see they are all their individual terms already, right? Okay, which is easier to integrate, or in this case, possible to integrate. Okay, once I split them up into two different fractions here. Okay, so then solve for this. Okay, so I'm going to use part 1 to help me solve for this. So when I integrate 2x plus 3 over x plus 1, x plus 2, okay, I'm going to split this up, okay, into integration of 1 over x plus 1 plus 1 over x plus 2. Okay, so when I integrate this term by term, 1 over x plus 1, this is basically my ln x plus 1. Okay, and then 1 over x plus 2 will give me ln x plus 2. Okay, then don't forget your plus here. Okay, so far so good. This one is just simple integration, okay, of your ln. Okay, the key thing here is to split these up into individual terms. Okay, so the previous time when we deal with polynomials, right? Okay, we have dealt with those that has just one single term at the bottom. Okay, so now if I have a multiplication of terms at the bottom, it will be hard for me to split them up into each individual fraction. Okay, so the only way I can do that is to use partial fractions. Okay, now let's take a look at another example, which I also need to use partial fractions. Okay, let's look at these examples. Okay, now it is just that the denominator, the factors are different types. The previous type is where my denominator are both linear factors. Okay, then I will split it up as a over x plus 1 plus b over x plus 2. Okay, so this next case, okay, is if, okay, first part, they want us to split this up into partial fractions, right? Okay, so here is missing a 15. Okay, so first, always check if this is a proper or improper fraction first. Okay, the degree of the top, okay, meaning the highest power is 2. Okay, then the degree at the bottom left. So I have a 2 plus x whole thing square here. It means this part will give me degree 2. Okay, then this part multiplied to this part, it means the highest degree here will be 3 because there's another x here. Okay, so the highest degree here is 3. Okay, so this is a proper fraction because the degree on top is lower than the degree at the bottom. Okay, so I don't need to do long division. Okay, so I can just straight away do partial fractions. Okay, so how do I split them up? First of all, let's look at the factors here. This is a repeated linear factor. Okay, so this is just a linear factor. So when I split this up, 3x squared plus 10x plus 15 over 2 plus x whole thing squared, 3 minus 2x. Okay, so for repeated linear factor, I need to have two terms to account for it. One with denominator 2 plus x, and the other one with denominator 2 plus x whole thing squared. Okay, so here I would have a over 2 plus x plus b over 2 plus x whole thing squared plus c over 3 minus 2x. Okay, so therefore the numerator, okay, 3x squared plus 10x plus 15, it will be equals to, okay, what is missing here is just another 2 plus x and 3 minus 2x, right? Okay, so a times of 2 plus x, 3 minus 2x. Okay, then what is missing in my denominator for b? It is 3 minus 2x. Okay, so plus b times of 3 minus 2x. Okay, then what is missing in my c? My c is missing a 2 plus x whole thing squared. Okay, so plus c times of 2 plus x whole thing squared. Okay, so let's use elimination method to try to eliminate either one of our a, b, and c's here. Okay, so by inspection, okay, we can tell if we sub in x as negative 2. Okay, if I sub in x as negative 2, this part will disappear. because 2 plus negative 2 will give me 0. So this whole part will disappear. And then similarly, this part, when I sub it in, it will also disappear. Okay, so when I let A and C disappear, I can find the value of E. Okay, so first value I'm going to sub in will be that x to be negative 2. Okay, so therefore after calculation, I will have 7 on the left hand side equals to 7b on the right hand side. Okay, so therefore b equals to 1. Okay, next, what am I going to let my x value be? Okay, I have a 3 minus 2x here and a 3 minus 2x here. So it means if I sub in a suitable value of x here and here, such that this part and this part equals to 0, I can find c. Okay, so what is the value of x here? It will be 3 over 2. Okay, so that x to be 3 over 2. Okay, then therefore this part will get 0, this part will also get 0. So consequently, a multiplied to this will become 0 as well, and b will also become 0. Okay, so on the left hand side, when I sub in x as 3 over 2, I will get 36 whole 3/4. Okay, then equals to 49 over 4c on the right hand side. Okay, so therefore this means our c equals to 3. Okay, next, how do I find the value of a? Okay, just substitute a simple value of x. Okay, you can sub in x as 1 or even 0. Okay, so let's do 0. Okay, so that it's easier to calculate that. So when I let x to be 0, okay, my left hand side will just be 15. Okay, then my right hand side will be 6a plus 3 times of 1 plus 4 times of 3. Okay, which is equals to, which means my 6a is equals to 0. Okay, so therefore a equals to 0. Okay, so now that I have my values of a, b, and c, okay, I will just sub it in to this part over here. Okay, so therefore, my 3x squared plus 10x plus 15 over 2 plus x whole thing squared, 3 minus 2x. Okay, since my a is 0, this part is gone. Okay, then my b is 1, so equals to 1 over 2 plus x whole thing squared. Okay, then my c is 3, so plus 3 over 3 minus 2x. Okay, so I've expressed this in partial fraction form. Then you will see why it helps. Okay, so originally like that, right? It looks like a very complicated kind of fraction. Yeah, which will be hard for me to integrate because there is no such thing as quotient rule, right? Okay, so therefore I need to use partial fraction to help me split this up into individual fractions. Okay, so that I can use either reverse chain rule or ln to help me integrate it. Okay, so part 2, hence evaluate this 3x squared plus 10x plus 15 over 2 plus x whole thing squared, 3 minus 2x. Okay, so I want to integrate this. Okay, so using part 1's answer, this is the same as integrating 1 over 2 plus x whole thing squared plus 3 over 3 minus 2x. Okay, so now let's take a look at these individually. Okay, for the first one, okay, let's split them up. So for the first one, it will be 1 over 2 plus x whole thing squared. Okay, so when I deal with this, am I going to use ln or reverse chain? Okay, it depends on the power here. So when I bring this up, this becomes 2 plus x to the power of negative 2, right? So I'm going to use reverse chain rule here. Okay, then how about this one? This one, the bottom basically means 3 minus 2x to the power of 1. So when I bring it up, it is negative 1. Okay, so therefore, with power -1, I need to use ln. Okay, so therefore, when I split this up, okay, let's split this up so that I can deal with them one by one. This becomes 2 plus x to the power of -2. Then the second one, I can take out the constant 3. Okay, so integrate 1 over 3 minus 2x. Okay, so when I integrate the first one, by reverse chain rule, I can just increase the power by 1. So it becomes -1 divided by the new power. Okay, then also divide by the differentiation of the inside, which is just 1. Okay, so I don't have to write it down. Okay, then for the second one, okay, I'm going to use ln because this one will give me a -1 as the power. Okay, so this is plus 3 times of ln 3 minus 2x. Okay, then don't forget to divide by the differential of the inside, okay, which is -2. Okay, then lastly put a plus c here. Okay, so when I simplify this, I will get -1 over 2 plus x. Okay, so I bring down this because this is negative power. Okay, then plus, oh no, minus. Okay, because this is a minus. Okay, so minus 3 over 2 ln 3 minus 2x plus c. Okay, so that would be my final answer. Okay, so always tell yourself, should I use reverse chain rule or use ln? Okay, so the case will differ based on your power. So if it's -1, you will always use ln. Okay, otherwise use reverse chain.